Previously here in Unit 6 we've been looking at basic thermodynamics, which says that energy change is due only to work or heat, and then we looked at the particulars of measuring heat, calorimetry. Today we're going to look at how this relates to chemistry. How is it that when physical changes take place or when chemical changes take place, chemical reactions, how is it related to things like stoichiometry and chemical change? An important part of understanding this is to understand the kinetic theory of matter. This is one of the most important ideas in all of science, that everything is made up of tiny particles, and these tiny particles are attracted to each other. So things like atoms, ions, molecules, all these little bits, everything that we see is made up of those things, and they have an attraction for each other. And then, as we've already discussed, as the particles jiggle faster, that means the temperature is higher. That's what higher temperature really means. And as they jiggle slower, that's what lower temperature really means. So that's a kinetic energy thing. But we also need to look at, during changes, what's happening with potential energy. Imagine that these little particles are attracted to each other, and we'll use a spring as our way of thinking about this. Two ends of a spring. As you stretch the two ends of the springs apart from each other, you store more energy in the system. So as the attractive particles are pulled apart, they store more energy in the system. The potential energy gets higher, in fact. Conversely, if we have particles that are held apart from each other and they're attractive, and we allow them to go closer together, well, that's going to be a release of energy. Now, let's apply this idea to some real-life situations. First, we're going to look at phase changes, physical changes, where you start and end with the same substance, just in a different form. And then we're going to look at chemical change. Melting, for example, is an endothermic change. Here's why. You can think about all the particles in a solid, like ice, for example, or wax, being all held together by these little springs, the attractive forces. So each one of these little red things represents a molecule of the substance that's in a solid crystal. And they're all held together by these attractive forces, which we are modeling as springs. When we melt a substance like wax, let's say, we're pulling all these particles slightly farther apart from each other. So in the liquid form, we've got the same particles, the same substance, but they're now stretched apart from each other. So it took energy to do that. And energy input had to be occurring in order for the particles to get farther apart. So melting something is endothermic. Energy has to go in to make it occur. Freezing is just the opposite process. It's just the converse. So you can imagine that freezing is exothermic. When something freezes, it gives off heat energy. This is the change. The liquid particles that are held apart are now allowed to come closer together as a solid forms. And so this releases energy. This is an energy out, an exothermic process. This is a little counterintuitive because we think of like ice freezing. We think of freezing happening in places where it's cold, so it doesn't seem like heat is coming out, but it is. If you put your hand behind a freezer, you'll notice this right away. It's hot back there because the freezer is constantly extracting energy from the interior. Now, the amount of energy that's absorbed when you melt and the amount of energy that's released when you freeze something is an identical quantity. And there's actually a name for it. It's called delta H, enthalpy change, of fusion. It's often abbreviated just delta H, FUZ, or since it's a heat change, sometimes it's called Q of fusion as well. This is going to be different from substance to substance, but every time a given substance melts or freezes, the amount of energy absorbed or released is going to be the same. And this is typically given in energy units per mole. For example, water has a delta H of fusion, this is for H2O only, is 6.008 kilojoules for every mole of water that you freeze or thaw. Vaporization is another phase change, and it's extremely endothermic. Think about liquid phase particles. Here are four particles that are kind of close together in the liquid phase. When you vaporize, they get much, much farther apart, thousands of times farther apart typically. And so this drawing isn't even really to scale. If this really was a liquid, you wouldn't, on this screen, probably have only one of these particles show up, and the others would be farther apart than that. So that's the gas phase. The particles have been moved much farther apart from each other. That took energy. So this is an endothermic process. Energy had to go into the liquid to make it turn into a gas. Condensing, just the opposite process, of course, is exothermic, because you're taking particles that are far apart, that are attracted to each other, and you're allowing them to move closer together as they become a liquid. Just like for fusion, the amount of energy that's absorbed during vaporization or released during condensation is the same amount of energy. It also has a name. We call this delta H of vaporization, or delta H vap, or Q vap. And for every substance, it has its own delta H of vaporization. Water, for example, like we had last time, has a specific delta H of vaporization. Delta H of vaporization for water is 40.79 kilojoules for every mole that you vaporize or condense. We'll use those numbers later. In all of the changes that we've just been discussing, what's happening is there's a change in potential energy, but there isn't a change in kinetic energy. Kinetic energy is how fast things are moving. Potential energy is energy of position, energy stored in where the particles are. So you stretch them apart, there's more energy. You let them go closer together, there's less energy stored in the position of the substances. So during phase changes like melting and vaporization, temperature is constant. Let's take a look at how this would graph out on a heating curve for water. On the x-axis, we've got how much energy has been added in kilojoules per mole. And on the y-axis, we've got temperature in degrees C. And I have a couple of significant marks here. One is 0, that's the freezing point of water, and one is 100, which is the boiling point of water. If we start out with some ice that's frozen and at some temperature below 0 Celsius, the first thing that happens is we will add energy to that substance and its temperature will increase in a straight line relationship. The amount of energy you have to add is given by specific heat of solid ice times the mass times delta T. So we've explored that quantitative relationship before. It's linear. The amount of temperature change is directly related to how much heat is added. And so you see this straight line that slopes up to the right. Once you hit phase change, however, the temperature does not rise. And so once we get to 0 degrees C for water, we're going to see the temperature flatten out, even though we're adding energy. You can see that there's been a distinct increase in the amount of energy that the substance contains, but the temperature hasn't gone up. What that means is the energy has all gone into potential energy, or energy of position, as the particles got moved farther apart, making liquid water. So this process here is melting. That's what's happening when this flat spot occurs. Q for this process is delta H vap times the number of moles. Once the solid is all turned into liquid, then the temperature can begin to rise. And we're going to see a relatively steep curve here because the specific heat of water is very high. But here the amount of energy added is, again, in direct proportion to the amount of temperature change. And this is the C of liquid water times mass times delta T that will determine how much energy got added. So direct proportionality again. Once we get to 100 degrees, we're at the point where there's another phase change. So we're going to see a flat spot. And now, because the delta H vap for water is much bigger than delta H of fusion, this flat spot gets even longer. And this is the process of vaporization. And the amount of energy that you have to add depends on the number of moles according to this equation. Q is delta H vap times number of moles. Once all the water is vaporized, then it's possible for the temperature to begin going up again. And so the amount of heat that's added will be proportional to the temperature change. And again, it's Q is equal to specific heat, this time of gas, times mass times change in temperature. So this whole heating curve is divided into 5 distinct segments. Here is heating of ice, melting here, heating of liquid water, vaporization, and then heating of steam or water vapor. So let's apply this to some problems. First question here is how much energy is required to vaporize 56.00 grams of water? Well, in those phase changes, Q is equal to delta H for the process, this is vaporization, times the number of moles. So the first thing we'll have to do is we'll have to figure out how many moles is 56 grams. So 56.00 grams, and it's water. You look up molar mass of water, you find out that it's 18.015 grams per mole. So grams drop out, and I will have a mole quantity for water that I can put in here for N. The answer is 3.109 moles. All right, so now I can calculate my Q. Delta H vap for water is... All right, so now I can calculate my Q. Q is delta HVAP times number of moles. Delta HVAP for water is 40.79 kilojoules per mole. And I'm multiplying that by the number of moles that I just calculated, 3.109 moles. Unit-wise, moles drop out, and I'm going to end up with kilojoules in my answer. And the number is 126.8 kilojoules. You try this one. Stop the video, try and figure it out. I'll give you an answer in a second. This is very much like the other problem. We know that Q is going to be equal to delta H of fusion times number of moles. So we have to find out how many moles we have, for one thing. We'll do that here, 24.3 grams of water, and water is 18.015 grams per mole. This will give us moles. The number to 3 sig figs is 1.35 moles. So Q is equal to delta H of fusion for water, that's 6.008 kilojoules per mole, times the number of moles that we just calculated, 1.35 moles. Moles drop out, the units are right, they're kilojoules, and to 3 significant figures it's 8.10 kilojoules. Here's another problem, slightly more complicated problem. Say you want to cool down some water, 500 milliliters of water, from room temperature, which is 25 degrees C, down to ice cold, which would be 0 degrees C, and we're going to do it by putting it on ice. What happens here is the ice melts, that absorbs energy, and it absorbs the energy from the water, and then the water will cool down. So we want to know what mass of ice would you have to melt in order to cool down the water. And the information that we have given here is water's density is 1 gram per milliliter. Let's start out this problem by drawing a little picture. Here I have my bottle of water, H2O liquid water, and then it's surrounded by ice, solid water. We know that energy is going to go from the water into the ice. So the water will cool down, and that will cause some ice to melt. The amount of energy that comes out of the water has to be equal to the amount of energy that went into the ice. So, how much energy comes out of the water? Well, the amount of energy that's released when something cools could be given by this: specific heat times mass times change in temperature. So that's going to be the amount of energy that's released by the water. But that has to be equal to the amount that's absorbed when the ice melts. For a phase change, like melting ice in this case, we know that Q is going to be equal to delta H of fusion for water times the number of moles that melted. So since Q water and Q ice are equal to each other, we should be able to set these two quantities together. C times mass times delta T equals delta H of fusion times number of moles. Well, what we're trying to find is the mass of ice that will melt. So we can find moles and then from there change that into grams because ice is water and we know water is molar mass. So solving this equation for N, here's what we find. N is equal to C times mass times delta T divided by delta H of fusion. Okay, C we know for water. The change in temperature is 25 degrees because it goes from 25 down to 0. Delta H of fusion is 6.008 kilojoules per mole. The only thing we don't know is the mass of water. But we do know its volume. And we know this: density is mass divided by volume. So mass would be density times volume. And the problem told us that the density of water is 1 gram per milliliter. And it also told us the volume was 500 milliliters. So that means we got 500 grams of water here. So now we're ready to plug this into the problem. So N is specific heat, which is 4.184 joules per gram per degree C, times mass, which we now know is 500 grams, times the change in temperature, which is 25.0 degrees C. We're going to divide this by delta H of fusion. Now, for water, that is 6.008 kilojoules for every mole. However, I have joules up here and kilojoules down here, so I'm going to want to change that. Instead of kilojoules per mole, I'm going to replace this with 6.008 times 10 to the third joules per mole so that my joule unit will cancel. So I just multiplied by 10 to the third, but I made it 1,000 times bigger is what I did, because there are 1,000 joules in a kilojoule. Now, if I look at what's happening to my units, now joules will cancel, degrees C will cancel here, grams will cancel here, and the only unit I have left is moles. Do my calculation to two significant figures, I find out that I have 8.7 moles. The last step is to turn this into grams. So I'll take my 8.7 moles and I'll multiply by the molar mass of water, which is 18.015 grams for every mole. And I'm using water because that's what ice really is. And it'll give me grams. To two significant figures, it's 160 grams of water.